How to solve the constrained optimization problem using Lagrange's method? The question is find the optimal bundle of good x and y given utility function of the consumer u is equal to xy plus 2x. X and y are the two goods subject to the budget constraint. That means 4x plus 2y is equal to 60. 4 denotes the price of good x, 2 denotes the price of good y, and total income of the consumer is 60. So what we want to do, we want to maximize the utility function of the consumer subject to his budget constraint. Okay. So first step in solving using Lagrange's method is what will we do? We set this budget constraint equal to 0, and here I have done it simply. After that, we multiply this budget constraint with lambda. Okay. Second step will be to form the Lagrange's function. So Lagrange's function is formed by adding this utility function with this resulting constraint. Okay, so we add the objective function and resulting constraint. To find the optimal values of good x and y, we partially differentiate this Lagrange function with respect to x and y and set them equal to 0 and solve them simultaneously. Okay, so first we partially differentiate this Lagrange function with respect to x. Derivative of x will be 1, so we are left with y. Derivative of x here is 1, so we are left with 2. Derivative of x in 4x is 1, so we are left with minus 4 times lambda is minus 4 lambda. Since we are taking partial derivatives, derivative of 60 and 2y will be 0. Symmetrically, L subscript y denotes the partial derivative of this Lagrange function with respect to y. Derivative of y is 1, so we are left with x. Derivative of the second term will be 0 because we are partially differentiating with respect to y. And here the derivative of y in the last term is 1, so we are left with minus 2 and lambda, so this becomes minus 2 lambda, and we also set it equal to 0. If this term is equal to 0, we set it y plus 2 is equal to 4 lambda, transposing this minus 4 lambda to RHS, and similarly transposing minus 2 lambda to RHS, so we get these two equations. Then we divide equation 1 with equation 2, so we have y plus 2 upon y, y plus 2 divided by x is equal to 4 lambda divided by 2 lambda. Lambda gets cancelled, 2 ones are 2 twos are 4, we get this very expression. Okay, cross multiplying, we have y plus 2 is equal to 2x, that gives us y is equal to 2x minus 2. Now we put the value of y into the budget constraint. Okay, when I put the value of y is equal to 2x minus 2, so we have 4x plus 2 plus 2. In place of y we have 2x minus 2, we set it equal to 0, sorry, equal to 60, that is in the budget constraint. Now this becomes 4x plus 4x minus 4 is equal to 60, or 8x is equal to 64. We get the optimal value of good x is equal to 8. Okay, to find the optimal value of good y, simply plug the value of x is equal to 8 into this equation. Okay, so in place of, we have y will be equal to 2 into the value of x which we got is 8, so we have y is equal to 2 into 8 minus 2, so we get y is equal to 14. So optimal values of good x and good y that the consumers should purchase or consume to maximize its utility is 8 and 14.